In this section, we are going to find a way to work with surfaces that are not just the graphs of functions. So something like z equals f of x, y. And I'll finally show you how to work with the surface command in GeoGebra that I've been using pretty frequently throughout the course. So one of the things that we talked about in this class is parameterized curves. So where we take some parameter t, and we use this we use functions for x, y, and z in terms of t. And frequently we'll put these all together in a vector valued function. Well, here we're going to, instead of using just a single parameter, we're going to have two different parameters. And usually, for whatever reason, the letters u and v are frequently used here. So if we have u and v, we might have x as a function of both u and v. So instead of having just a single function of two variables, here we have a different function of two variables for x, y, and z. And of course, we can have a vector valued function version of this as well, where r of uv has these components. X of uv, I, let me go ahead and just write them down here, y of uv, j, and z of uv, k. We can pull these u and v from any region in the uv plane. So we'll have an entire plane here of u's and v's. We can have some domain D that's in uv, and that turns into a surface in three-dimensional space. So you end up getting some surface here that is the graph of that D in the XYZ space, where a particular point here might map to a point on that surface. So going through an example of this probably is the best way of tackling it. So here we're taking the function r of uv. It has components of u, v cubed, and negative v. We have limits on our u's and v's. Now note here that what we've essentially done in our uv plane is just take a square. So going from -2 to 2 on both of our axes. Now, of course, our domain doesn't have to be a square or a rectangle, though a lot of our problems we will do that. It'll be a lot easier to work with rectangles in general. And in fact, a lot of times we'll specifically set up our surfaces to make it work out that way. When we actually get into GeoGebra and start trying to graph this thing, so keep in mind what we have here, u v cubed negative v. Our surface command is actually going to specifically work with rectangles most of all. So I type surface, I type in my three components. Those were u, v cubed, and negative v. I have to tell it what variables I'm using because we don't have to use u and v here. You want to avoid using things like x, y, and z, but u and v are safe choices. So my first variable is going to be u, and then immediately after I type in u, I'm going to type in my limits for u. In this case, that's -2 to 2. Then I'm going to get my other variable, v, and I'm going to tell it the limits for v as well. And I close that up, and I get this surface here. Now, one thing you can notice about this right away is that GeoGebra put a grid on our surface. In fact, you may have noticed that every time I've used this command in the past, GeoGebra always puts some sort of grid on the surface. Sometimes the grid is a little less obvious. If we look at problem 9, this is another surface with components of u cubed, u sine v, and u cosine v. U is going from -1 to 1, v is going from 0 to 2 pi. If I graph that one, and I'll kind of hide that one for the moment. So again, I do surface. My components are they're u cubed, u sine v, and u cosine v. Again, I need to tell what my units, my variables are. We have u going from -1 to 1. We have v going from 0 to 2 pi. This one's a little bit smaller than the other one. But again, there's a sort of a grid here. There's showing various curves on here. We've got these curves going out along this, and then we've got this circle going around here. And so it may not be as obvious that there's a grid there, but there is one there. And those are not just for show. What they are actually doing is showing us the graphs of curves where we use the actual formulas here, but keep either u or v a constant. Let's go back to problem 8. We're going back to this one here. If I take this particular surface, so I take this particular equation here, and we'll fix maybe u equals 1. If I set u equal to 1, then we have r of 1v is equal to 1 comma v cubed negative v. And I can plot that as a curve where it's a curve because we have a single actual variable put in here. We have a single v that is our parameter for a curve. We don't have any other variables involved here. This is just a curve, and we still have the v going from -2 to 2. If we graph that curve, just using the curve command, so we're giving it v, and we're going from -2 to 2. And where did it show? Okay, there. It is there. It's just really hard to see it because they made it not very visible. Let's make that thicker. Okay, there we go. So we have this curve here. This is it. If you notice, it actually does follow one of our grid lines, or grid curves, you might say. That's what all of these curves on here are. These are all the graphs of curves like this where they've chosen a particular constant value for u. Now you can probably guess here that I guess this one right in the middle is where u equals 0. This was where u equals 1. This on the end would be where u equals 2. And I guess they did it by thirds. I don't know why they chose thirds, but that's the way it went. If you instead let v be a constant, so here if we instead fix v equal to 1, then r of u1 this time, so here the u is still there, but now v cubed is 1 cubed, so 1, and negative v is -1. The u is still going from -2 to 2. So if we go ahead and plot that curve, so it's u1, -1, variables u going from -2 to 2. And of course they're going to make me have to make it thicker this time so we can actually see what's going on. We get this particular curve going across. So we've got the other grid curves by making v equal to a constant. And each one of the lines going across are now the v equal constant lines. And I guess they did those by thirds as well. This would be 2, this would be 1 2/3, 1 1/3. Those are the values that they chose to plug in for v or for u, depending on which direction you're going, to get those particular grid lines. GeoGebra will even allow you to use the previously defined functions in the curve command. So if we want to make one of our lines going across on this surface here, the surface was defined as the function a. That's the letter they automatically chose. If we replace the x, y, z in here by a of, say, let's say when let's say v equals -1 this time. Or let's actually replace the u. Let's replace u by -1. Well, so we'll put in -1v. We still have to tell it what the variable is. It's going to be v, and we still have to give it the limits. So we don't get it around that part. And of course, they are still going to make it thicker. There we go. So this is the particular grid curve where the actual u value is -1. You can actually, it even shows you the full function, and then it shows you what's being plugged into that function. So kind of some neat things that you can do with GeoGebra when it comes to parameterized surfaces. A lot of how we will handle anything involving parametric surfaces will depend on how we can work with the grid curves. For instance, let's look at a tangent plane to a parameterized surface. So we'll say our surface is R of uv, which has components of x, y, and z. We're going to pick a point on the surface. So we'll have some. Actually, let's even draw a picture of this. So it's over some domain D. It's being mapped into some surface in three-dimensional space. We'll call that surface S. There's a point on our surface that we want to look at. We'll say that's the point x0, y0, z0. And it comes from some point in D, which has coordinates of u0, v0. And actually, maybe I want to have a... Let's actually move this out of there. I'm going to put this off to the side so I can draw stuff in my picture. So the point there is u0, v0. But what I'm going to do is I'm going to look at those grid curves. So those grid curves were made by looking at constant u values and constant v values. Those are vertical and horizontal lines in the UV plane, and they're the lines that go through this particular point. Those end up being some curves on our surface. They don't have to be perpendicular to each other on the surface, but they will cross in some way. We're going to say that C1 is the curve where we're basically letting the u value be the constant u0, but we allow the v to actually change. Technically here our components are u0 v, u0 v into x, and the same thing for the other ones. So now this is an actual curve where the parameter is v. The u0 is just a constant that's being plugged in there. We'll also let C2 be the one where the v is a constant v0. So I guess in this particular picture, assuming that we kind of have the same orientation here, where we've essentially taken this thing here and kind of just pulled it up into three-dimensional space, we can say that this one here is C1, that's the one going this way, and then the one going across is C2. As curves, we know how to find tangent vectors to these particular curves at that point. Remember, we just take the derivatives. But keep in mind that since we are using functions of more than one variable, we're going to be using partial derivatives. Not that that really changes anything about how we find them, other than the fact that we need to make sure that we're keeping the other variables constant, or the other variable in this case constant. So for the tangent vector to C1, we would take the v derivative. So the derivative with respect to v which is the derivative of x with respect to v, derivative of y with respect to v, and the derivative of z with respect to v. Technically, we want the vector actually at the point, the point that x naught, y naught, z naught, or the graph of the point u naught, v naught. So we end up replacing now the v here with v naught after we've taken the derivative. So technically, all these derivatives are at u naught, v naught. Though a lot of times we are just going to refer to this vector as r sub v. So here, we all it's really saying is that we've taken the derivative with respect to v. We'll kind of suppress the of u naught, v naught, just because it can get a little messy when you've got a lot of stuff going on. And we're going to be using this vector here pretty frequently. Now this was for C1. If we look at C2 instead, now our variable here is u, so we differentiate with respect to u. We get r sub u, doing the exact same thing, except now all the derivatives are with respect to u instead. That's the only thing that changes here. And just like we did with r sub v, we're going to call this r sub u. And so these two vectors are going to play very important roles. If we make kind of a more zoomed in picture of our surface, we have our point here. This is, you can say it's r of u naught, v naught. And maybe we have one vector coming off here. This would maybe, I guess to keep in the same format that we have here, I said C1 was the one that goes like that, and that was the one that gave us RV. So we could say this one is the vector RV following that curve. Then we have another vector RU. This is following the curve C2. But these are both vectors coming off of this particular point. And these are both tangent to our surface. So our surface is somewhere around here. If we want to get any other vector at this point that is tangent to the surface, it's going to be in the same plane that's determined by these two vectors. And so we want to be able to find the tangent plane, or the plane that's determined by two vectors. Now, normally that will be plenty. Normally that's exactly the amount of information that we need to determine a plane. However, the one thing that could go wrong here is that r sub u and r sub v could be parallel vectors. If that's the case, there are many different planes that pass through those two vectors, and well, we wouldn't have a unique answer to this problem. So we're only going to be working with surfaces that don't actually do this, and we're going to call such a surface smooth. So RU and RV are not parallel. And let's make that V look more like a V and less like a U. I want to keep those separate. This is a V. So how do we determine if a surface is actually smooth? How do we know if this doesn't happen? How can we make sure it doesn't happen? And for that matter, how do we turn two vectors into the equation of a plane, if we have that? We have to think back to chapter 12. Recall that one thing that we did is we took a normal vector to a plane and turned that into an equation. So if some vector here, this is going to be an n, let's just say this has components of a, b, c. If this is normal to a plane, then an equation for that plane will look something like ax plus by plus cz equals d for some number d. Or you could also write this as a times x minus x naught plus b times y minus y naught plus c times z minus z naught equals 0, where x naught, y naught, z naught is some point on that plane. Either way is a way to do that, but getting a normal vector to the plane allows you to get this equation, or either one of these equations, pretty easily. So if we have two vectors that are in the plane, can we get a vector that is orthogonal to both of them so that new vector is going to be normal to the plane? Well, we use the cross product. If we have two vectors, then the cross product of those two vectors is actually normal to those two vectors. Or you can say orthogonal to those two vectors. So what we're going to do is take r sub u cross with r sub v. This is a vector that's perpendicular to both ru and rv, and therefore it is normal to both the tangent plane and you could say to the surface itself. In fact, you could say that's the kind of the definition of what it means to be or normal to the surface, is that it's normal to the tangent plane. In the worst case scenario, this could be the zero vector. Except if the cross product of two vectors is 0, that's exactly the case where those two vectors were originally parallel, which is exactly what we do not want to have if we have a smooth surface, or a smooth parameterization of our surface. So this condition here, that these are not parallel, is going to be equivalent to saying that r sub u crossed with r sub v is not equal to the 0 vector. In fact, we'll basically take that as our definition. If this is not equal to 0, then our parameterization is smooth, and since it's smooth, then we can use the cross product to find the tangent plane. So let's take a particular surface and find a tangent plane at a particular point. So our surface here has components of 1 minus u squared minus v squared, then minus v and minus u, and we want to find the tangent plane at -1, -1, -1. Let's first graph this thing. So we're taking a surface. It has components of 1 minus u squared minus v squared, comma minus v minus u. Our first variable is u. Well, they didn't actually give us limits on u and v. Let's just pick some big range for u and v, and it'll probably be far enough. So there's no issue with our particular equations here. These functions actually do have domain everything, so I'm just going to go from -10 to 10. And that'll actually send it off the screen. We don't have to worry about where the edge of our surface actually is. V is also going to go from -10 to 10, and we have this shape here. In fact, it is actually a paraboloid. We're looking at the point -1, -1, -1. That is the point A, sitting right there on our surface. We want to find the tangent plane to our surface at that point. Now, before we even begin taking any sort of derivatives here, we do want to actually figure out what are the parameters at this point. This is the x naught, y naught, z naught from before. We don't have the u naught or v naught that we need to plug into here to get that point. So we first need to see what u and v make -1, -1, -1. Or in other words, when is 1 minus u squared minus v squared equal to -1, negative v is equal to -1, and negative u is equal to -1. Well, these last two equations kind of give it away. That's when u is equal to 1, v is equal to 1, and plugging those into here, 1 minus 1 minus 1 does give us the -1 we expect. So this is going to be the numbers that we plug into our function. We go ahead and find our derivatives. R sub u, we differentiate each of these components with respect to u. So the first one, the 1 goes away, the v squared goes away. Derivative of negative u squared is a -2u. That's our I component. There's no u in the j component, so we can kind of leave that out, or you could put plus 0j if you want to. Derivative of negative u is a negative 1 times k. So negative 2ui minus k is r sub u, or at least in general it is. If we're looking specifically at this particular point, we plug in 1 and 1. Well, that just basically changes that, gets rid of that u essentially. We have negative 2i minus k. Moving on to v, doing the same kind of thing. Well, this first one, we get a negative 2v this time. The negative vj becomes a negative j, and the negative uk becomes a 0. So again, going ahead and plugging 1 and 1 into that, we end up with a negative 2i minus j. And I'm just going to refer to these two vectors here as r sub u and r sub v from this point on. I'm going to suppress the 1, 1 part of that. Let's go ahead and plot these vectors, though. So remember, they start at the point A. That's what they name that point. I'm just going to use that. We're going to have a vector that starts at A and then is modified by the vector negative 2, 0, negative 1, because that's negative 2i minus k. So that vector is coming off there. Let me make that a little bit thicker so we can see it better. Then we'll do the same thing with the other one. So we have the vector starting at A and being modified by negative 2, negative 1, 0. And again, let's make this a little bit thicker. So we have these two vectors that are definitely tangent to our paraboloid. There you go. They are definitely not perpendicular to each other. So don't expect your r sub u and r sub v to always be perpendicular to each other. They definitely can be, but they don't have to be. We want to find a vector that's orthogonal both of those, so we'll take their cross product. So ru cross rv, so we have negative 2i minus k cross with negative 2i minus j. Of course, we get to essentially FOIL this out. If these had all three components for both of them, I might have went ahead and used the determinant method. But since it's just two terms in both, it's pretty easy to FOIL them out. Negative 2i crossed with negative 2i, because the i's are parallel to each other, they're the same vector. That cross product is 0, so we don't even have to worry about that one. We have negative 2i crossed with negative j. So we could say 2i cross j. We'll worry about what that is in a second. We have the negative k crossed with negative 2i. So that turns into plus 2k crossed with I. And then finally, negative k crossed with negative j. That's plus k crossed with j. Well, I'm going to start with the k crossed with j. K crossed with j is actually a negative I. So if you remember the circle for this, if we're following the arrows here, we get a positive version of what's next. If we go backwards, we get a negative version of it. So if we go from k to j, we end up going backwards to I, so we get a negative I. If we look at 2k cross I, ki, if we follow that, we're following the arrows to a positive j, so we get a plus 2j. And then finally, the 2i cross the j, ij gives a positive k, so we have plus 2k. So the vector negative 1, 2, 2 should be orthogonal to both ru and rv. Now if we go ahead and plot that vector in here, so this vector starting at A and then being modified by negative 1, 2, 2, and we make that a little bit thicker so we can see it better. we definitely have something that is orthogonal to both RU and RV. You may be a little bit surprised, though, that it does point inside. You might have expected it to point outside. That has more to do with the order that we have our variables. We did R sub u cross with R sub v. If we did R sub v cross with R sub u, we would actually have the other direction. Remember, switching the order in a cross product introduces a negative sign. So there is a kind of orientation that's actually coming into play here, and we're going to actually need to worry about that a little bit later. Especially when it comes to things like Stokes' theorem and the divergence theorem, it's actually going to cause not cause some issues, but it'll be important to pay attention to. But for the moment, we're not going to really worry about that. It's not going to come into play when we look at the tangent plane. But the point here is that this vector here is normal to our tangent plane. That means we can go ahead and find the equation of the tangent plane by using those as coefficients, and we take x minus, well, we're taking the negative ones here, so x minus negative 1 plus 2 times y minus negative 1 plus 2 times z minus negative 1, that it will equal 0. Or basically, we just have negative x plus 2y plus 2z. You can move all the constants to the other side, or you can start with this and not bother putting the negative 1's in there and just plug in the point that you have. We plug in negative 1, negative 1, negative 1. We get a 1 minus 2 minus 2, and we get a negative 3. So either way you want to go about doing it, that's how we'd find the tangent plane. And if we go ahead and graph that plane, we have negative x plus 2y plus 2z is equal to negative 3. And there it is. It's perfectly touching that point at touching the surface at that single point exactly how we wanted it to. So I'm going to go ahead and leave this video here. There are definitely more things that we need to talk about here, but I do want to not have these videos drag on too much. So I'll talk about ways of getting parameterizations for various surfaces in the next video, and if that goes on long enough, maybe we'll even have a third video where we'll talk about the surface area of a parameterized surface. So meet me in those videos as well.